We've got a linear programming formulation question, but this time it's for the allocation problem. It's not about the Hungarian algorithm here. However, the first part of the question, where it's talking about maximizing the income, this could appear as a part A of a question, where in part B you went on to use the Hungarian algorithm to solve this problem here. However, we're not using the Hungarian algorithm here. We are going to be in part B basically set it up as a linear programming problem so that the simplex method could be used. So that's it really. We're going to, so for the part one of the part A could easily come in any question on allocation problem, whether it be a linear programming formulation question like this, or whether in part B you went on to actually use the Hungarian algorithm to actually solve it. Because as we know, the Hungarian algorithm actually minimizes the income. So let's just deal with that part first. We're looking for the largest number here. The largest number in this box, as we can see, is the 257 there on the right hand side there. Okay, now that means that we can change it by taking all of these numbers away. So let's write up our table here. Task 1, task 2, and task 3. And Harriet Jason, and Catherine. And we're going to take each of them from 257. So this number here will then be 0, because 257 take away 257 is equal to 0. The number in this box here, we're taking 243 from 257. So that equals to 14. And the number here, we're taking 251 from 257. So that equals to 6. The number here, we're taking 244 from 257. So that's 13. And the number here, we're taking 247 from that, and that's 10. And we carry on through the whole lot of them. So just to change the number, so 249, take 2 from 257, that equals to 8. And 252 from 257, which equals 5. And 246 from 257, which is equal to 11. And that is it. Only 1 mark. Of course, it would be a lot quicker because you would be given the table in the examination. Okay, so that's the first part dealt with. As I say, that would be quite commonly seen with using the Hungarian algorithm for the part B, but we're not doing that here. In fact, we don't need to use it at all for part B. Now, you could in part B of the question, which gets us to to set this up as a linear, use these numbers and say minimize as our objective function. However, do remember that these are not actual costs here. They are relative costs, if you like. So it might actually be sensible to revert back to the original numbers and just put maximize in our objective function. So long as we say maximize cost or whatever, then we're fine. Okay, so let's go on and do that. And so we need to think about what we're doing with the allocation problem here. Now, we've got this kind of Xij. We need to notation which will help us come up with our decision variables. Okay, now the allocation problem either Harriet does task 1 or doesn't do task 1. So it's quite different to the transportation here, where we talk about number of units being transported from one place to the other. So either Harriet does task 1 or she doesn't. If she does do task 1, then she doesn't do task 2 or task 3. So she can't do all of these tasks, she does one of them only. So how are we going to represent this numerically? Because either she does do it or she doesn't. Okay, and the way we actually do this is to use binary coding. So 1 representing that she does do task 1, and 0 representing that she doesn't. Okay, so we're going to use the IJ notation again. So we would call this making H stand for Harriet. This one could be XH1, this one could be XJ1, and this could be XK2, K1, sorry, and so on. And this one would be XH2, and so on. I won't go and define them all, but if you've got lots of them, to actually label them all with different letters can be quite time consuming. I know we've only got 9 here, so it's quite doable, but we may as well actually do this in a kind of neater, more pure mathematical way. So what we do is we say, let Xij be equal to, and we have this kind of binary thing go 0 if, now I represents one of the workers here, doesn't it? Harriet, Jason or Catherine. So if worker I does task, and J is actually representing the task here, task J. But of course that's not defined, of course. It does not do task J, of course, because 0 represents does not do task J. Okay, and 1 if worker I does task J. Okay, so make sure we get those the right way around, not. But 0 being not. Okay, so we haven't fully defined them yet because we haven't said what I and J is, where I is one of the workers, and we just need to list the 3 workers. I would be careful here and actually take the effort to write each of the names down. You may get away with putting the letters, but I think it's always better to be cautious with these things. So let's put the actual names down. I is one of the workers, and J is the tasks. And we've got possibly task 1, 2, 3. Or 3. Okay, so we've got our decision variables is now well and truly set up. Okay, so now we're going to, we can either talk about the constraints or the objective function. Certainly makes sense to do decision variables first. But let's just now look at the constraints. Now, the constraints here, of course, it's all to do with the fact that these 3 numbers, for example, one of them has to be equal to 1 of XH1, XH2, and XH3. Okay, one of them's got to be equal to 1, but only one of them, one and only one, has got to be equal to 1. So these three numbers here have to add up to 1. These, not the 251, of course, because if these numbers are actually equal to 1 or 0, and they've got to add up to 1. So we could write out the numbers, and it wouldn't be too bad here because we're only going to write 3 of them out. But I think it is quite a good idea to use the sigma notation, because if there's 4 of them, then or 5 of them, it actually just makes it nice and quick to do, and it actually makes it less likely that you're going to make a mistake as you don't mess up with the variable or whatever, because the consistency of the variable and the definitions are going to be checked very carefully. So we can say for constraints, let's do this row first. This row first. They've got a total 1. I'm going to use sigma notation, and if I just say x, h, j equals 1. Okay, and sigma and we can do these 3 as well. Similarly, that would be sigma x, j, and that's capital J, not to confuse with the little j. A little bit confusing, but that's capital J for Jason. So, and let's just put a j here because that's the thing we're summing over. Okay, trying to get the j looking like a capital J there, equals 1. And the sigma j of xk j equals 1. So those are all the 3 rows done. All those 3 rows are done. Okay. But now what we might want to do is we might want to look at the column. So if we look at the column constraints, we're now looking at the fact that these have got to fit. Task 1 needs to be allocated to one of them. So one of these numbers is going to be equal to 1, and the other 2 is going to be equal to 0. So in other words, they're going to total to 1. So therefore, we have now noticed this time it is the I that the second bit that's staying the same, task 1. The 1 bit is staying the same this time. So we can say sigma x, and we're going to go xi1 equals to 1. And now we're summing over I. And similarly, we can sum these 3 together. So that's going to be sigma I of x I2 equals 1. And then finally, the final 3, these 3, one of them is going to be 1, the other 2 are going to be equal to 0, is going to be sigma I xi3 equals 1. Okay, so that's our constraints. Notice here, however, that there is no need for, in fact it would be inappropriate to give a non-negativity constraint. You'll remember when we looked at the linear programming formulation for the transportation problem, the non-negativity constraint was very important. But here we've already defined our xij to be equal to 0 or 1. So to say that xiy is greater than or equal to 0 is at best unnecessary, at worst inappropriate. It's not really wrong, but it's certainly inappropriate. I've no idea whether that would be penalised or not, but it's certainly inappropriate. So I just would not put it there. But so long as you remember that in the transportation problem, And in the game theory problem, the non-negativity constraints are necessary. Okay, so we need to write down our constraints. Not constraints, we need to now write our objective function. Now, as I said earlier, I'm going to just stick with the original numbers here and use the word maximizing, because that's what the problem was that's what the original problem was about. If I go back to the original problem, it was about maximizing. The fact that the Hungarian algorithm minimizes is kind of neither here nor there, because we're not doing the Hungarian algorithm. We're maximizing and we're formulating it as a linear programming problem. So it wouldn't be really wrong to use these numbers here and minimize, but you would have to say minimize in your constraints. Okay, and of course in that situation it's questionable what the actual values would represent. Okay, so let's go back to looking at the constraints of the objective function. You can send them the other way around. It's often the objective function is given before the constraints. I've always personally been in the habit of doing it the other way around. Don't think it matters. So the objective function is to maximize, and we'll call it C. Now we need the coefficients. I'll rub all this out now. We need these numbers together with all the suffixes associated with them, all the letters. So we're going to have to write all 9 of them out very carefully with the coefficients. 251 times by xh1 plus 244 times by xj1 plus 249 times by xk1. I'm going to write the next one on the row below. So I'm going to start writing these ones on the row below. Just a nice check to check that it's all lined up properly. Plus 243 xh2 plus 247 xj2 plus 252 xk2. You can see that lining up like this is a kind of nice check to see that it's all right and the suffixes are all consistent. And so finally we'll do the last column. So let's do these 3. Okay, just taking very great care we don't write any of the numbers down sillily. I will probably at the end of this check that my numbers are all written out correctly. So now it's xh3 plus 255 xj3 plus 246 xk3. Now that is our linear programming formulation. It's worth actually spending time now. Obviously that should get us full marks hopefully in the exam. It's worth checking that all our numbers are right. I looked down the columns 251, 244, 249. And I can see 251, 244, 249. 243, 247, 252, 243, 247, 252, and then the final one, 257, 255, 246, 257, 255, 246. It might have actually been sensible to do columns and then rows, and it might have actually been more consistent, but it might have been easier to check. But so long as we have some way of checking that our suffix, check your suffixes carefully. So to do this, there's sufficient marks in this. Remember, you've had 7 marks here. I've taken a lot of time to talk you through this, but it shouldn't actually take that long. But it does really deserve respect. You need to spend that 10 minutes or so checking that everything's right and proper with these types of questions. Now, it's also note that these numbers here, our decision variables, are 1 or 0. So only 3 of these numbers in total, only 3 of these terms out of the 9 terms I have in this expression here, only 3 of them are actually going to be equal to 1. 6 of the other ones are going to be equal to 0. Well, that's exactly what we want. We want, because we're going to have only each person is going to do one task, or each task is going to be done by one person. So only only 3 of the numbers are actually going to count. In actual fact, if we look down the columns here, if we look down, one of these numbers here is going to be equal to 1, and the other 2 are going to be equal to 0. One of these is going to be equal to 1, the other 2 are going to be equal to 0. One of these is going to be equal to 1, and the other 2 are going to be equal to 0. And we could likewise do the same with the rows. Okay, one of these is going to be equal to 1, and the other 2 are going to be equal to 0. Okay, so that is it. That is the linear programming formulation of the allocation problem.